Okay, this next video lecture will be on sketching atomic orbitals, molecular orbitals, and molecular orbital energy diagrams. We'll start off by talking about atomic orbitals. Atomic orbitals are represented using a simplified contour plot, using shading to indicate the negative parts of the wave function. So for an S-type orbital, we can just represent the orbital with a circle, with sort of a single contour around a darkened point that indicates the position of the nucleus. For P-type orbitals, there's some directionality. So sometimes they're going to be sketched, say, along this axis, again with a darkened point in between, and the negative lobe can be represented using shading. So again, we're using sort of a single contour, and this approximates this full three-dimensional shape of the p orbital, which is this sort of blob of electron density, or this wave function that has positive portions and negative portions, and there's a nodal plane between the positive and the negative portion of the orbital. So we could say this would be, let's say, maybe the PZ orbital. For px, we could have it going along the x-axis like so. And here it would, the negative part of the wave function will be represented by the shading of the lobe that's to the left. And there's going to be another one that we can represent as maybe either sticking outside of the plane of the piece of paper or tablet, or kind of along an angle. That's not so good. Let me try it again. Something like that, where it's maybe at an angle, and we'll call that PY. And again, they're represented as a sort of single contour line and with shading to indicate the sign. Now when we move on to molecular orbitals, it gets a little bit more complicated. First of all, we've already looked at the S case. Let's look at that again. What we often do is take the atomic orbital or the atomic orbitals and sketch them on the left, say like so, where if we had, in the case of hydrogen, we'd have two 1s orbitals, maybe one on nucleus A, the other one on nucleus B, and we could sketch them like so. Those are the atomic orbitals. However, as we noted when we were working through the H2 plus molecule ion, they combine to form bonding or anti-bonding orbitals. And so if we take 1sa plus 1sb, that's going to give us this overall molecular orbital that looks a little bit like this. And if we looked at 1sa minus 1sb, that's going to give us an orbital that looks a little bit like this. Notice the difference between atomic orbitals and molecular orbitals. These over on the right-hand side are the molecular orbitals. Now, in some classes, they sketch molecular orbitals to look just like atomic orbitals. There's no real indication of bonding. There's no real indication of where the nodal planes are. There's very little, if any, representation of sign. Here, we've tried to take into account the fact that there's electron sharing occurring in the bonding orbitals, in that we end up with a sort of single contour for the bonding orbital, and it encompasses both nuclei. In the case of the antibonding orbital, there's a sign change between A and B. Also, it sort of looks like there's this nodal plane that I've indicated here with a dashed line, and it looks like the electron density is sort of pushed away from the nodal plane. Although that's not a physical force that's pushing it away, it's just the fact that the symmetry of the wave function, constructive and destructive interference, gives rise to this reduced electron density in between the two nuclei, as indicated by the nodal plane, as indicated by the fact that the probability density is sort of skewed to either side of the nucleus. And so in the context of this course, this is what I'm looking for when I'm asking for a molecular orbital for the case of, say, 1s. Now, when we want to combine p orbitals, things get a little bit more complicated. First of all, let's look at a case of, can we combine a 1s atomic orbital with, say, a pz atomic orbital, something like this. And the answer is no. Whenever we're combining atomic orbitals to make a molecular orbital, both sets of orbitals, both orbitals, need to have the same symmetry with respect to rotation about the internuclear axis. So that wouldn't work. However, we could, in principle, combine a 1s orbital, or say a 2s orbital, with a with a 2p orbital that's aligned along the internuclear axis, and here that axis would be the x-axis, and if we change the sign on this so that we flip the sign on that orbital, then this could give us an overall molecular orbital that would look a little bit like this, where we've lumped one lobe of the 2px orbital in with the 1s orbital, but the other lobe is going in the other direction. And there's a sign change there that we indicate with shading. We'll talk about other rules regarding how orbitals are combined later. And in particular, there can be issues of the relative energy levels of the atomic orbitals that can determine which orbitals can mix and which ones don't. Now let's look at some more combining of atomic orbitals to make a molecular orbital. Let's look at 2px A plus 2px B. Again, I like to start by sketching the atomic orbitals on the left and then look at the resulting molecular orbital on the right. If we have this orbital here on A, this orbital here on B, and we combine them, in between the two nuclei, there's going to be some cancellation of charge. And so the resulting molecular orbital is going to reflect that. We're going to have small lobes here, relatively speaking, and then larger lobes here on the other side of the nucleus. See, this one's going to be minus sign, this one would be positive, this would be minus, and then the next one would be positive. There would be an additional nodal plane here that's perpendicular to the internuclear axis. And this is an antibonding orbital. Now, if we subtract the two, then we would flip the sign on one of the atomic orbitals. We'll pick the one on the right. And then we end up with this kind of molecular orbital where in between, since the signs are the same, we have this constructive interference. So we have this kind of expanded, larger lobe here that's in between the two nuclei. And we have smaller lobes on the outside. So this is showing some electron sharing in this region between the two nuclei, and this is a bonding orbital. Now let's go back and maybe label some of these. We call this A plus B 1s orbital a sigma 1s orbital. The antibonding orbital is sigma 1s star. We'll ignore that one. This would be a sigma 2p star. And this would be a sigma 2p orbital. These orbital label classifications use sigma to represent what we can typically think of as a sigma type bond. These are for molecular orbitals that have a sort of spherical symmetry with respect to rotation about the internuclear axis. We'll move on to pi bonds later. The star indicates whether or not it's bonding or antibonding. So if there's a star, it's antibonding. Again, back up to this one. This is an antibonding orbital. Antibonding orbitals typically have a nodal plane, like in the case of this one, that is perpendicular to the internuclear axis and that resides somewhere between the two nuclei, typically near the middle. Now let's look at the pi type bonds. If we looked at a 2pz plus 2pz, our atomic orbitals are going to look like this. The combined molecular orbital, there's different ways to sketch this. It kind of depends on where you pick the contour point when you're doing a contour plot. But one quick way to sketch it is to show a cloud of shared electron density that's a little bit to either side of the internuclear axis, and nevertheless shows some sharing, even though the electron density is not directly, is in fact completely excluded from the internuclear axis because of the underlying 2pz orbitals. However, there's still in this kind of region here in between the two nuclei, there's still a fair amount of electron density, and so we can think of those electrons as being shared, or that electron is being shared between the two nuclei. This is a pi 2p orbital. Now if we flip the sign on one of those, then there's going to be a different sort of interference pattern that we see in the resulting orbital. We're going to have this additional nodal plane here, which is going to push the electron density out a little bit away from the nuclei. There's a nodal plane there, and we shade the orbitals thusly. Notice whenever there is a nodal plane, there has to be different signs of the lobe of the orbital on either side of that nodal plane. So there's going to be an opposite sign for these. There's another nodal plane, of course, that's due to the 2p orbitals themselves that's along that axis, and that's going to indicate that you're going to have a different sign there as well. And this is a pi star 2p orbital. Another way of representing these orbitals is that we can sometimes call them Gerada and Ungerada. So you can have things like sigma 1s, sorry, sigma g 1s. That helps to remind us that this is a Gerada type or even type symmetry orbital, and the parentheses tells the atomic orbitals that it's made from, the say 1s. The antibonding orbital is sigma star u for 1s. and you could write it using sigma u star 1s. So using these symbols, we can keep track of whether or not a particular molecular orbital is has even or odd symmetry with respect to inversion, and we can keep track of whether it's bonding or antibonding, and we can keep track of the atomic orbitals that it is made up of. So applying that treatment to the pi orbitals, we have pi Ungerada, say 2p z. That is our bonding orbital. And it is odd with respect to inversion because, as you see, if you invert along the z-axis, you change the sign. So it is odd, even though it's bonding. So there's no simple mapping between, oh, Gerada is always bonding and Ungerada is always antibonding. It depends on whether you're dealing with sigma or pi. Similarly, there's no simple rule that says sigma is always S and pi is always P. If the p orbitals are aligned along the internuclear axis, then it's a sigma bond. Okay, then the antibonding orbital is actually going to be pi g star. It turns out it has even inversion symmetry because you have to invert along both axes. So when you invert along one of those planes, you flip the sign of the wave function, but then if you invert along, if you mirror it along the other plane, it'll flip the sign again, and so the overall end result is even. So this is a pi star g antibonding orbital that we see right there. And again, that's 2pz. And I alluded to this classification scheme a little bit more, or a little bit previously. Here I'm going to go into a little bit more detail. We say lambda is the number of nodal planes containing the internuclear axis, then L for that, the angular momentum, is going to be plus or minus lambda, plus or minus lambda h bar. And our scheme is that when lambda is 0, we call that sigma. If lambda is 1, then pi. And if lambda is 2, then we have a delta orbital. So that's a bonding or anti-bonding orbital made from d orbitals, which are something that we will not cover in this course. The sketches get rather complicated. And again, star for antibonding. And the other thing that we need to keep track of is G and U, which stand for even and odd symmetry. Okay, and that's the end of this lecture. Next, we'll talk about the second row, homonuclear diatomics.